All right, so we were discussing why it is that we expect certain things to happen and not other things. All right, and we said it had to do with probability. So with that in mind, suppose that we're given n atoms and molecules with m accessible states. And we'd like to know in how many ways can we put n1 atoms, molecules, in the first state, n2 in the second state, and so on and so forth. Well, I mean, more or less obviously, this is given by our n atoms, and I'm going to put n1 in the first state, n2 in the second state, all the way up to nm in the last state. Right? That's what I'm going to do. And so what I'd like to do is extremize this function. But before we do that, let's discuss the nature of this quantity. This quantity depends on the state of the system. In the standard terminology of thermodynamics, the states of the atoms are referred to as microstates, and the system is referred to as the macro state. All right? And so what we're looking at here is a single macro state, all right, consisting of n1 objects in the first energy state, n2 in the second, n3 in the third, all the way up. All right? Now, this is a state variable. So now we could ask, is it intensive or extensive? And remember, to answer that question, we have to consider two systems, and we have to consider what happens when we put them together and make one system. So let's suppose that we had system 1, which had 10 different ways that it could occupy its states, and system 2 that had 15 different ways that it could occupy its states. In how many ways could the collection of the two systems occupy? Well, I mean, there's 10 ways that the first system can occupy, and for each one of those 10, there are 15 ways that the second system can occupy. That means that the system together, the collective system, would have 10 times 15, 150 ways. And that's because we're thinking of the two systems as independent of one another. But that's not extensive or intensive. Extensive was supposed to add, not multiply. Intensive was supposed to be the same. It's clearly not that. So what could we do? What can we do to change multiplication into addition? Of course, the answer is we're going to take a logarithm. All right? If I combine two systems together, the logs of the number of ways that their state can be occupied will add. Okay? Because the number of ways multiplies. So for that reason, we introduce the extensive state variable S. S is equal to conversion constant, pay no attention, all right, times the log of omega. This is an extensive state variable called the entropy of the system. Okay? As you've heard in other classes, the entropy is a measure of disorder. The more ways in which a state can be filled, the larger the entropy. Okay? The more likely it is that that state will be the state that you find the system in. The larger entropy. Okay? So now all we're going to ask is, how can we maximize the entropy? Well, more or less obviously, the entropy will be maximized. I'll get absolute maximum entropy when I have the same number of atoms and molecules in each of the states. All right? We spread it all around evenly. Now that's all well and good, but in reality, these energy states have a different amount of energy that they require for each state. And I only have a certain amount of energy available to me. So what I'd like to do is extremize the entropy subject to two constraints. All right, my variables are N1, N2, N3, all the way up to Nm. All right, I need the sum of all those to be capital N. I only have a certain number of atoms, molecules. All right, I also need to be subject to a constraint associated with energy. I didn't write down the energies of these states here, so let me just write them. There. State K requires energy epsilon K. So the appearance of epsilon is because I wanted something that was like energy, E. Uppercase E is going to be the total energy. Lowercase e is spoken for. So we're going to use epsilon. All right? And there we go. So I'm going to extremize the entropy subject to these two constraints. The total number of atoms, molecules is constant, and the total energy of the system is constant. All right? So let's see what we got up in here. We're going to define our function capital F as I'm going to ignore the K-Boltzmann for the time being. All right, it's just a constant, and I'd rather just not write it for the time being. All right. All right, so I've got my log omega plus lambda, sum of the mk's minus capital N, plus I need another Lagrange multiplier. It's standard to use the next letter in the Greek alphabet, which is mu. This is not to be confused with the chemical potential, which is also often discussed in problems involving the first law of thermodynamics and all this thermodynamic stuff, which also uses a mu. We're not going to be working with the chemical potential in this class, so I feel safe using mu. But some of you may be looking at other things that do use a mu. Please do not confuse the chemical potential mu with our Lagrange multiplier mu. It's only going to be here for a couple of minutes, then it's going to go away. All right? Placeholder. So, there we go. All right? Now, in order for us to use Lagrange multipliers to find the extreme value, I'm going to need to take derivatives. All right? And that's going to be awkward with the factorials. Okay? So it might not surprise you that we're going to go immediately for Stirling. All right? We're just going to go straight for Stirling. And we're not going to feel bad about it at all. Because when we were using Stirling before, for like 10 or 15, now we're looking at the occupation number of an atomic state. All right? So we're talking 10 to the 10 at the very least. Okay? So I'll write it out without Stirling, but then Stirling's coming. All right. So when I do df by dnj, okay? All the n's are independent of one another. That's the beauty of introducing the Lagrange multiplier associated with the constraint, the sum of the n's equals capital N. That constraint is going to impose that. That means that I can think of them as completely independent of one another, because the constraint is going to be imposed at the end. All right? So, I mean, it's just like when we were looking at our ellipse, we didn't have to worry about x and y having to satisfy the equation of the ellipse when we were looking at the derivative of f with respect to x and f with respect to y. We just let them be whatever they want. But then when we solve the system, the constraint equation is one of the equations. All right? That's the role of lambda and mu in this equation. It's to impose a constraint. So I don't need to worry about interrelationships between the different n's here. So I'm just going to say this is minus the derivative with respect to nj, natural log j factorial. When I take a derivative here, I'm just going to get lambda. When I take a derivative here, I'm going to get mu epsilon j. And then SC equals 0. All right? Now, what is this derivative? So, Stirling gives us this. All right? When I take a derivative, I get a derivative of nj times log of nj. That's log of nj plus nj times 1 over nj, that's 1, minus 1, that cancels, plus 1 over 2 nj. All right? Now, as we said, nj is a large number. So I'm going to ignore the 1 over 2 nj. And I'll just have natural log nj. Okay? All right, so let's see what it does. Amazingly, this solves the whole system immediately. All right? So my equations give, I'm going to get rid of this here and just minus log nj. All right? So I get that. Now, I could do this for the jth term, and I could also do it for the ith state. So I have lambda plus mu epsilon I is equal to the natural log of ni. All right? Or if I wanted to, I could write it like this. Log of nj minus mu epsilon j is constant. Okay? So I could view this as the natural log of nj e to the minus mu epsilon j is constant. All right? So that means nj is proportional to e to the mu epsilon j. All right? Now, when I write it this way, it turns out that mu is going to be negative. All right? Because if mu was positive, it would mean that states that require more energy have a higher occupation number than states that require less energy. Okay? Now we'll find that there are some physically very difficult systems to excite that do have that property. We'll talk about that later on. All right? But what we'd like to do now is figure out what it is that this mu represents. Okay? So we find that the number of atoms in a particular state is exponentially dependent on the energy that state requires. All right? And this mu tells us the relationship between the energies that are accessible, or not the relationship, but like the line, the dividing line between ones that are accessible, where this exponential factor doesn't suppress the occupation that strongly, and states that are inaccessible, where this exponential completely suppresses the occupation. All right, so we'll talk about that on Thursday. All right, everybody have a wonderful afternoon.